Hello everyone. First of all, let me introduce the member of our group, Roberto Duque, Jose Vargas, and me, Gabriel Muñoz. This is our final Clil presentation for the subject Dynamics and Vibrations. Our topic is the evolution of the space industry. Uh, Now let's take a look at the table of contents. We will start with a brief introduction to the topic and its relevance in the context on aerospace engineering. Then we go to the three clear tasks that we complete this semester. After all, we will present our conclusion and finally our list of reference. Uh, the advancement of space technology demands systems capable of operating under extreme conditions where dynamics, both kinematics and kinetics, plays a fundamental role in the design and control of aerospace. Accurate motion and force analysis is key to ensuring functionality and resilience, especially in a microgravity or failure scenarios. This presentation highlights the central role of dynamics in modern space applications by examining trajectory corrections, deployable linkage, and solar array system, demonstrating how dynamics principles enable innovation and mission reliability. The Clil 1 is about orbit injection strategy under failure conditions. Uh, this research addressed the autonomous decision making and trajectory planning, or ADMTP, which is a major challenge in a space mission, especially during launch vehicle failures. In aerospace engineering, dynamics play a central role in describing how a system reacts to changing force, especially in critical conditions like engine failures. In this study, the dynamics of the vehicle, position, velocity, acceleration are continuously monitored and adjusted in real time to maintain mission feasibility. To make fast and accurate decisions during a failure, the authors use a radial basis function neural network, B no RBFNN. This model learns from simulated dynamics, behavior, and predicts orbital parameters in milliseconds. It's training using physical data generated by simulation based on dynamic laws, showing the power of combining AI with classical mechanics. TDOS stands for Target Degradation Ordnance Strategy. This method enables the system to reduce the mission target, like changing the orbital altitude or dropping payloads, while preserving safety and functionality. Um, Then we have the ATU ETM, means Adaptive Target Update, an iterative guidance method. It updates the trajectory in real time by calculating position errors and adjusting the injection point. This is based on dynamic equation and control theory. Compared to the older methods, ATU EGM improves precision and speed, which is essential in fast evolving flights environment. Now my teammate is going to talk about the Clil number 2.
Hello everyone, I'm Jose Vargas. I'm going to talk about the four-bar linkage mechanism using in the space industry. Now for the next slide, we have the next one, please. Thank you. Uh, no, the before. Yeah, we have the rocket launch platform. Talking about of the using of the four-bar linkage, it well done of the using of the rocket launch platform, where NASA is one of the largest exponents of the space industry, with mission of constant evolutionary improvement. This configuration can be used for stability and motion control, and if a platform needs to slightly change the rocket angle before launch, a four-bar mechanism can provide a smooth control style or angle of the links. The next slide, please. Well, we have the Grashof law. The Grashof law for the four-bar mechanism uh, gives us sorry give us as such as mobile arms of a rocket launch platform. Sorry, if the condition S plus L minus equal to P plus Q is met, one of the links can rotate completely, where we have the S as the shortest was link, the L as the longest, and P and Q can be is the other two. This allows the arm to retract smooth, highly, and continually when release the rocket before launch. Now for the next slide, we have the vector analysis, where we have the in the right image, we have the vectorial loop. Well, we have the vectorial position, sub 1, sub 2, sub 3, and sub 4, and the angle of these links, the theta sub 1, theta sub 2, theta sub 3. Well, the theta sub 4 doesn't break here, but it's 0. And for the next slide, we have the moving equation for a four-bar linkage where we use, I don't say before, the Euler method. So for that, we have the position equation, velocity equation, acceleration equation. And we have the two equations for the real ones and the imaginary ones. For the position equation, we have the c sub 1 times cosine of theta sub 1 plus c sub 2 times cosine of theta sub 2 minus c sub 3 times cosine of theta sub 3 minus c sub 4 equal to 0. And for the imaginary one, we have the c sub 1 times c sine of theta sub 1 plus c sub 2 times sine of theta sub 2 minus the c sub 3 sine of theta sub 3 equal to 0. Now for the velocity equation, we have to derive by time the position equation, so we can introduce a next new expression. We have the angular velocity, sorry, as we can see in the real ones and the imaginary ones. Now for the acceleration equation, we have to also derive by time the velocity equation, so we have the a new expression that are alpha. Alpha is the angular acceleration. So for this, we can know that for example, the c sub 1 times of alpha sub 1 times the sine of theta sub 1 are the tangential acceleration of the mechanisms in that link. And also we have the minus c sub 2 times omega sub 2 squared times the cosine of theta sub 1, or theta sub 2, sorry, where we have the normal acceleration of the link in the second link, sorry. And this can be expression of the other one expression in the two equation that we have. So my teammate is going to talk about the array solar system.
Hello, my name is Roberto Duque. I'm going to talk about the array solar system. And well, these systems are essential for supplying energy to satellites, the space station, and exploration missions by converting solar radiation into electricity in environments where terrestrial power sources are unavailable. These traditional solar arrays have faced several challenges: high mass, limited storage efficiency, and mechanical complexity during deployments. Over time, innovative mechanisms have emerged to overcome these limitations, and today we will discuss three of them: the 1964 Scissor type system, the SpaceX modular panels, and the rollout solar array, or ROSA. Next slide, please. The first one, let's begin with the positive deployable solar array deployed by Fairchild Healer in 1964. This system used a scissor-like extension mechanism with flexible panels and was one of the first successful mechanical designs for autonomous deployment in space. And well, following with the dynamic analysis in the next slide, we have the free body diagram with three forces. And well, assuming that we have a symmetrical system, it is necessary to analyze just one link. And we can define the potential energy, the elastic potential energy, as the half of stiffness multiplied by the square of position. Then we have the kinetic rotational energy, which is the half of inertia multiplied by the square of the angular velocity. And then, assuming that we have no energy losses, the conversion is ideal. And then we have that the elastic potential energy is equal to the kinetic rotational energy. And due to the absence of external torques, the system angular moment L is equals to the inertia in function of time multiplied by the angular velocity in function of time, which will be constant. And the resistive torque T sub F will be equals to minus C sub F, which is the coefficient, friction coefficient, minus C sub F multiplied by the angular velocity. And the equation of rotational motion becomes in inertia multiplied by the angular velocity derivated by time, which is equals to minus C sub F multiplied by omega. Next slide, please. And then we have the SpaceTech Solar Arrays, the second system, which was developed by SpaceTech GmbH. These are lightweight, modular, and highly efficient solar panels designed for harsh space environments. What makes them special? Well, they offer power densities up to 3,020 watts per square meters with a reliability above 99.99% and can provide up to 5 kilowatts of end-of-life power. Their deployment use rigid links connected by torsional C-springs. And for the dynamic analysis, in the next slide, we have the free body diagram with 4 forces. And then, assuming that we have a simplified model, like in the previous system, with n rigid link of mass and m and length L connected by n-1 torsional springs with stiffness K, the total elastic potential energy stored in the C-springs is given by the summatory of the half of stiffness multiplied by the square of theta sub j in time in function of time less the theta sub 0. And as the mechanism unfolds, the stored potential energy is converted into kinetic energy. The total kinetic energy of the system is the summatory of the half of inertia sub j multiplied by the square of angular velocity sub j, plus the half of mass sub j multiplied by the square of velocity sub j in the center of mass. Neglecting to friction and external forces, the system followed the principle of mechanical energy conservation, which means that the kinetic energy in function of time plus the potential energy in function of time will be the initial potential energy. Next slide, please. And finally, we have the roll-out solar array, or ROSA, where we have the most advanced system developed by NASA and deployable space systems. This is lightweight, flexible solar blanket that deploys using 2 extendable booms called stems made of carbon fiber reinforced epoxy laminate. For the dynamic analysis, in the next slide, please. We have that if the boom is modeled as a thin cylindrical shell of mass m and radius r, rotating with angular velocity omega, its rotational kinetic energy is expressed as the inertia multiplied by the square of angular velocity, which is equal to a quarter of mass times the square of radio multiplied by the square of angular velocity. And then the total mechanical energy released during deployment is distributed at the total of energy, which is equal to rotational energy plus the E sub lim plus the E sub this. And this analysis also allows an estimation of the torque generated by the boom using torque T equals to inertia plus the angular acceleration. Next slide, please. For the conclusion, we have that the evolution of deployable solar array system reflects a clear shift from heavy motor-driven structures to lightweight, efficient, and passive deployment mechanisms from the early scissor type array in 1964, which introduced spring power, motion and braking control, to SpaceTech's modular design offering high power, density, and structural resilience. Each innovation addressed key limitations of earlier systems. Finally, we have the references, if you need to see it. And that's it. Thank you for your attention.